biomechanics is the first topic of today. As I learned, most of you have a bioengineering background and probably know already something about mechanics, continuum mechanics, and application to biology. However, to bring you maybe on the same page and to clarify a bit the background of biomechanics, I thought it's a good idea to start with the basics, with the very basics. I assembled a few slides here, I must say, and then I was shocked to see that it's more than 50 slides, and I don't think I can make it through this all details here with you within the next 1 hour. So I don't want to overstretch here the seminar lecture. We also want to discuss, and you are of course encouraged to ask questions just right away. And therefore, I suggest we go as far as we get. Right? And if there are further questions, we have then overlapping topics in the following lectures. For example, medical imaging, MR elastography, what we do, our basic diagnostic techniques here we are developing. This all has roots in biomechanics, and you will always recognize the equations or the approaches, the structure actually of the physics and the mathematics behind.
Thank you. Man muss richtig aufrufen, man kann nicht so gut fahren. Die anderen müssen noch ein bisschen lauter sprechen. Aber ganz gut fahren. Ich glaube, das voll, weil es sieht das irgendwie so. Das Vorbild.
One important point, this lecture will be recorded, so personal things, please announce and we switch it off and switch on again, or we can confidential and personal things also discuss within the breaks, right? And the rest will be publicly available afterwards. So when does the recording start actually? It has already started, okay. Yeah, so the audio system is also not very perfect here in the room, so meaning I'm well to understand, but if you ask questions, maybe you speak up a bit louder than normal in order to get understood here online. It's okay, I think we can go with that. Just try to stick here with the slides. It doesn't work. Did you kind of switch it in or? Okay, then I do it manually. I think it's again the battery. Okay, doesn't matter. I can also progress this here. It's a mouse, it works. Okay. Maybe we find another solution within the break. Okay. Let's start simple with the statement that biomechanics is systemic, meaning it affects the whole body from the toe to the brain, and it does it constantly. So always, if your body encounters waves, deformation, motion, it affects the whole soft tissue in the body, and this is transmitted by biophysical signals, because biophysical signals are long-range signals. So waves, for example, coming through the leg to the brain can activate receptors which lower your blood pressure within the brain. Therefore, jogging, running is healthy. So this has just been published recently in Nature. Very basic observations from our daily life, which come more and more into the awareness of biologists that those biophysical signals change something with the environment where cells respond to and react to. And many of these signals are transmitted by biomechanical parameters. And biomechanical parameters of soft tissues in the living body are overly complex. And it's the question where to start with, actually. So the tissue we are dealing with is always heterogeneous. So it's just a matter of the scale. If you zoom in, you will encounter a hierarchy of structures which goes down to the cells, and your fingers can feel this hierarchy of signal conversion from the micro scale to the macro scale. So this is a high, or the background of the high sensitivity of palpation, that we feel the connectivity of cells. And this is all related also to the non-linear response of the tissue. The biotissue is always non-linear elastic, never only linear elastic. So this brings in parameter quantification a huge level of complexity into our equations. So therefore, also here we need to make simplifications. Well, viscoelastic means it's not only elastic, it's not, so soft tissue is not vibrating after tipping on it like jelly pudding, right? So it's easily damping off vibrations and mechanical stimuli. And this is actually the haptic distinction between a chunk of meat actually and pudding and jelly, which can be equally soft with a very low shear modulus. However, in the damping, both materials are distinct. They are really different here. And this is viscosity. Well, anisotropy, it's always there. It's just a matter of the scale. On a large scale, muscle is a good example for anisotropic biotissue. And poroelastic means we have multiple phases, actually. So solid phase and liquid phases intermerged and mixed on a micro scale. However, we see it on a macro scale as an effective medium, and this is all covered by the theory of poroelasticity. And to understand a bit this complexity, we need to understand the basic concepts of mechanical stress, strain, the elastic moduli. This is already all in the Hooke's law. Then the viscous damping of waves, for example, as we use waves as a physical contrast medium in elastography. Well, decompressibility is an assumption. Poisson's ratio gives, as I will show, different stretch relationships in different directions. And of course, the concept of poroelasticity. So that, why do we care? I already said the biomechanical properties are important for diagnosis, for example, palpation. I think since the late Paleolithicum, when the humans started touching and sensing after the Great Leap, when our brains changed and we could suddenly speak. So this is something which we don't understand yet, what happened 50,000 years ago. But since then, at least, humans are able to touch and to explain what they feel with their fingers and to use this as a diagnostic means. So this is, for example, documented in the Ebers papyrus in Leipzig. If you come to Leipzig, just a 1 hour drive by train here. So it has a great Egyptian museum, and there is a great medical book, the first and most ancient medical book, the Ebers papyrus, where explicitly the hardness, the stiffness of tumors is treated or explained in the chapter. Well, and mechanobiology actually, so I just click further here. Mechanobiology, I already mentioned, is very important and increasingly recognized as being important, as cells differently react and respond to differently stiff environments. And not at least the scaling, as I mentioned already, so shear modulus is a scaling property which is communicated over multiple levels of the hierarchy in tissue. And biotissue has a hierarchic architecture, and this is exactly which makes the shear modulus so sensitive to disease on a micro level, communicated on the macro scale. And this is all actually reflected by this broad range of values we can measure with the shear modulus in the living body over 10 orders of magnitude, from almost zero in blood to bone hard. Actually, we can encounter or observe almost all values of the shear modulus. And this is quite rare in solid state physics to have such a parameter, right, which has such a huge bandwidth, especially in living systems, in us. Therefore, of course, there's a huge motivation to harness this parameter as a diagnostic means. Compared to that, relaxation times in MRI are quite limited in their range, so they go back to the content of water and to the mobility of the water within tissues. So soft tissue has a huge amount of water, so I will show the table later, but there is no free water in soft tissue. It's all bound somehow, or at least immobilized. So it's not strongly bound. It's hydrogen bridges which immobilize the water due to the very high content, volumetric content of glucosaminoGlycans, GAGs, in the tissue, which are polar substances. So especially sulfated GAGs, just the abbreviation of glucosaminoGlycans. So they bind a huge amount of water, and this has also a mechanical function. It's a kind of resistant shock absorbing system to pressure, to compression. While proteins, which are more elongated and stretched and interconnected to a fibrous network within the ECM, the extracellular matrix in soft tissue, they more restrict the tissue to shear stretch, to shearing. So compression and shearing, so we have now already the two basic modes for deformation of the body, which goes back then to Hooke's law. Well, so as I mentioned already, so we have an amount of approximately 75 to 80% of water in our soft tissues. So as a fun fact, the kidney has more, nominal, very small amount, but more water than blood. And here you see already how important the structure is. The water content itself is not making up the mechanical properties, the resistance to shear, which is zero in blood, but the kidney, as Ariane knows, has a shear modulus in the order of, I would say, 4 kilopascal, something like this. So this is a huge difference, and this comes due to the architecture, actually, with proteins, with how the cells are organized, etc. And this makes the shear modulus so sensitive. The kidney, by the way, is one of the stiffest organs in the abdomen, in the abdominal cavity, maybe followed by the spleen, but the spleen is only stiff because of the pressure inside the system, then followed by a healthy liver. As if you have a cirrhotic liver, then buenas noches. Your liver has maybe a stiffness of 10 kilopascal or even higher, so this can then be the stiffest organ. And one of the softest organs is a pancreas, and it remains soft over lifespan, while pancreatic cancer is very stiff. So it's really illuminating or very bright, intense in the elastogram, in the stiffness map. Therefore, detection of pancreatic cancer with elastography is a hot topic. Well, the density, by the way, is almost always taken as a density of water. So with 75 to 80% water, we can easily accept that the density is around 1 kilogram per liter of water. Unit density maybe a bit higher with accounting for the proteins and other structural elements. This is different, of course, with two tissues in the body, which is this cancellous bone, so spongy bone, has air in it and lung. Right? So whenever we have cavities with air, the density of the biotissue is much lower than that of normal water-containing soft tissue. Well, let's start here with the very first and important and initial parameter we could measure actually when we go to biomechanics, and this is a deformation. To measure stiffness and stress, for example, in tissue, you need to deform the tissue. And the deformation is a quantity which has already relationship to the intrinsic mechanical properties and can also be used as such a parameter if you normalize your deformation. Deformation is displacement normalized by the size of the deformed object. And you have two ways to deform the tissue. You can shear the tissue and you can compress the tissue. Whenever you do palpation, you wouldn't compress the tissue. Palpation means shearing tissue layers against each other. So you test the shear modulus, never the compression modulus, and never try it actually, because this hurts. If you compress the tissue, then your object of investigation will start yielding. But shearing is at least with a low deformation or low displacement amplitudes, is a safe operation, as our body tissue is made to attenuate shear deformations actually. Whenever your body encounters shear waves, which come through all kinds of processes in daily life, cycling, for example, on cobblestone, or sitting next to a laundry machine, this all induces shear waves, mostly in the range of 20 hertz to 30 hertz. And these shear waves are very effectively attenuated within the body. So this is due to the viscosity. And this is by design, by nature, important, because shear waves would target the tissue and destroy it and impair. Therefore, we need here viscosity as a very important biomechanical properties of tissues. Well, and how can I go back actually? Yeah. Okay, compression, shear deformation, and the shear deformation has two modes actually, which is axial deformation and shearing deformation. And the axial deformation in an incompressible material means that you have lateral deformation if you press axially on it. So we cannot distinguish this, and both is related to each other, the shear modulus versus the so-called Young's modulus, which is the parameter that is tested by axial deformation. Well, in a very simple way, I think the most simple way to bring it down to mathematical equations, the strain tensor can be deduced from the deformation gradient. You all know multiplication of two vectors can either be in a scalar product way or in the cross product way, where you either reduce the dimensionality to a scalar, two vectors come to a scalar. So a vector is a rank 2 tensor actually, right? And if you multiply a tensor rank 2 with a tensor rank 2, then you end up with either a tensor rank 1, which is a scalar, right? Or with a tensor rank 4, right? And this is with a cross product, a matrix. It can be represented here as a matrix. Therefore, the which I showed the infinite notation, the deltas replaced by this derivative operators here from the gradient. You should point to it. Okay. So this is the gradient operator. So in all spatial directions, 1, 2, 3, or x, y, z actually. And this is the displacement, right? You can now normalize the displacement, which is also directed into the Cartesian axis of this three-dimensional space, right? You can normalize this again into three spatial directions, and you end up here, therefore, with this deformation gradient or deformation matrix. And the linear part of the Lagrange strain tensor is the symmetric part, or the symmetrized deformation gradient, actually. So this is a very simple procedure. And by the way, this is the strain tensor we use for all our analysis. If you go to higher order terms, it gets overly complex. So therefore, we stick here to this linear symmetric strain tensor. Well, and as I said, this already tells you something about the properties of the tissue. For example, if you take one invariant of the strain tensor, which is a divergence, so the sum of all axial or diagonal strain elements here, right? So this is a derivative 1 by x1, 2, 2, 3, 3, and you sum them up, then you know already the compressibility of the tissue, if this tissue is compressible or not. And this is an important measure because it relates to the pressure in the tissue. Pressure is compressive stress. I will come to the stress tensor in a minute. So this is an important quantity, and it's related to the compression field. A compression field has a source term, meaning if you calculate the curl of the field, which is a combination of all non-diagonal derivatives, then this curl of the field is 0. While vice versa, the shear field has no source term, so it's a curl actually, right? And the divergence of this field is 0. And this is the idea of the Helmholtz decomposition of the wave equation, that you can separate the compression field from the shear field and vice versa. The only drawback here is that we have to apply derivative operators, which are numerically sensitive to noise. Therefore, we normally, groups do it, and we did it in the past to apply the curl operator to our wave field in order to be sure, okay, we are analyzing here shear waves and no contribution of compression wave. Well, and the compressibility can be parameterized in the Poisson's ratio, which is actually the ratio between different axial stretches or strains. So if you assume compressibility, right, then the axial strains are 0, meaning pressing here onto the z-axis, the 3, 3, or the 3-axis, then this strain, right, is balanced by the lateral strains, right? So this means with the assumption of incompressibility and the assumption that these strains are equal, then we come to a Poisson ratio of 0.5. This relates to incompressible materials and isotropic materials. In case of anisotropy, we have here a factor which is the Young's moduli ratio along these axes to which the strains pertain, and therefore the Poisson's ratio of an anisotropic material has no bounds. So we cannot say it's a upper bound for an incompressible anisotropic material is 0.5. We cannot say this because this depends on the ratio of the Young's moduli, and these can be arbitrary, right? So therefore, no bounds for anisotropy and Poisson's ratio. Interestingly, there are even materials which expand laterally when you stretch on, right? And those oxalic materials, honeycomb type of materials, can be designed and have been designed. And this is just a little fun fact that this Poisson's ratio can also be smaller than 0. Well, I find it quite interesting to see that materials which have a regular shape, which looks like quite isotropic, like such an cubic lattice here, right, is an orthotropic lattice. This is not isotropic because it does not resist shear, right? So if you would build up a house in such a way, then it would crack with the first slight wind from the side, right? It does not support shear and resist shear deformation, and therefore this whole lattice is not isotropic. Isotropic is just if you add here such diagonal elements, or you can also design other shapes, but they should isotropically support axial deformation and shear deformation to come at all to this assumption about isotropy. And here you see already that real tissue is never isotropic. So if you zoom in, you will always find irregularities, like here shown in these simulations, when you have some gaps within the lattice, for example, and you stretch on it, then you will anisotropically deform the lattice and support it on different degrees the diagonal elements, and the shear modulus will be different depending on the direction you pull on the overall lattice. Well, and this is an important point because normally in elastography, the Young's modulus is assumed to be related to the shear modulus by a factor of 3. So assuming isotropy and this incompressibility, this Poisson ratio of 0.5. And this is obviously not the case if you at least come to better resolutions, and you can also see different levels of the hierarchy of the architecture. So this wouldn't be anymore a valid assumption. Well, stress, similarly to strain, is a symmetric tensor. By the way, why is it symmetric? I mean, this is a fundamental physical principle why strain, stress, etc. are symmetric tensors. You know it? What would happen if this part here, 1,3 stress component would be different to 3,1 or vice versa? If you push against the surface, right? So this is a force you apply to a surface.
Oh no, I mean, I was just gonna say, like, every force has an equal and opposite reaction, right? So it's just a consequence.
Exactly, it's not balanced.
It has to be, right? Like
It has to be balanced to
Yeah.
deform, to elastically deform. Otherwise, you would start rotating the body, right? So this is the principle that it's symmetric, and the same applies to the strain tensor. So to exclude rotation and non-elastic deformation, it has to be symmetric, and this defines the strain energy function actually. So the product of all components of the stress tensor with the strain tensor and their sum up, because energy is a scalar, right? So, and all components of stress and strain, so all kinds of deformation you have applied to your body, define the potential energy you have invested into the material in order to deform it. And if it's a pure elastical material, so this energy is stored and can be recovered, right? Therefore, the shear modulus is also called the storage modulus. So the stored elastic energy, and this is this W here. So this defines actually how we describe our Hooke's law here. And this is a linear elastic equation. This is the simplest representation of Hooke's law. It's also a very complex material law, right? As you see here, it's a fourth rank tensor. So second rank tensor strain, second rank tensor stress, and the proportionality is a fourth rank tensor has to be, right? And fourth rank tensor has many independent components. So without any physical implications, for example, the symmetry of stress and strain, we would have 81 elements. So it's just the number of elements in the fourth rank tensor, 3 to the power of 4. With the symmetry of stress and strain, we have 21 independent elements. So this would be, I think, the cubic symmetry of the material. Well, and if we come to orthotropic materials, which have 3 symmetry planes, we have 9 independent elements, which is 3 shear moduli, 3 Young's moduli, and 3 Poisson ratios. Then the next level towards isotropy is a transverse isotropy, where we have isotropy in one plane and one principal axis. And here we would have only 5 independent elements. And if we additionally make the assumption of incompressibility, then we end up with 3 independent elements. So no Poisson ratio. This is all related to the Young's moduli. 3 independent elements, 2 shear moduli in the isotropic plane, in the plane of symmetry, plus 1 Young's modulus, or the ratio of Young's modulus. You can represent this in different ways. Well, in isotropy, 2 independent elements, shear modulus and compression modulus. And if we additionally make the assumption of incompressibilities, then we end up with 1 parameter, which is the shear modulus, and this is our basic parameter. Okay. Well, this is a representation of Hooke's law, already with the expansion here in the nonlinear behavior. So Hooke's law in general assumes the linear slope here between stress and strain, and the slope is the, well, are the coefficients of the elasticity matrix, right? And if you have here a nonlinear behavior with increasing deformation, strain, or stretch, then you would need to look into small deltas of your stress versus delta strain, because then these coefficients become dependent on the strain, right? The bigger the strain, the higher the slope here. So this is important. That's a delta stress divided by delta strain gives you the coefficient here, the C, and this delta determines actually what we measure. I find this the most compact form of a very general nonlinear material flow, but it's not very practical. You see here. So this is a kind of Taylor expansion of Hooke's law. So Landau came up with this formulation, but well, as you see here, we have quadratic terms in the formerly linear strain tensor, and here cubic terms, and this makes it unhandleable. So what can I do actually with a measure which depends on the strain I apply to? So whatever I measure here, it's not only the intrinsic non-linearity of the tissue, it's deformed differently as more I press or I strain the tissue, the higher order terms here become into play, and this makes it unhandleable. Therefore, different other approaches have been proposed here for nonlinearity, but just to give you the structure of the ideas, Hooke's law is a general simplification of such a Taylor expansion of the nonlinear stress-strain relationship. Here's an interesting study, quite old, from 1992, which showed, I thought, for the first time, so that you see, of course, a nonlinear response here in muscle tissue, tension versus the initial radius, which is strain, kind of strain. And well, it's very nonlinear actually. The more you stretch, so you will approach the nucleus, destroys the tissue. So, but before that, it's increasing dramatically in the felt and excellent and tested stiffness of the tissue. But interestingly, if you digest the cells out here and end up with a decellularized tissue, muscle tissue, then you can also digest the elastin fibers within this ECM, and you see an even more enhanced nonlinear behavior of the muscle tissue. While if you just look at the elastin fibers, then it's almost linear elastic. So this already shows the function, the biomechanical function of collagen versus elastin. Well, and I already touched upon this several times. So we are using waves to test the mechanical properties, and waves are deflections, local deflections. So we vibrate the particles in the tissue around the origin of a static coordinate system. Therefore, we can use here the conservation of momentum equation, which is a Navier equation as an extension of Hooke's law. So this is relatively easy to solve, while the Navier-Stokes equation is a full equation which also considers or takes into account the movement of the coordinate systems. Therefore, you need here materials derivatives, and this is this additional term here, which makes solutions almost impossible. I think the Century solution objective is dedicated with $1 million prize money to solve or to find solutions, analytical solution for Navier-Stokes equation, which is so far not the case or not possible. The Navier-Stokes equation is important for all MRI techniques which measure flow. So this can be done as with MR elastography, flow in the aorta, aortic arc, for example, or within the ventricle, the left ventricle of the heart, etc. Beautiful techniques which end up and show beautiful streamlines of the fluid, which is propelled through the vessels. But well, we have it in elastography easier because we know our coordinate system is static, and so we can stick here to the Navier equation. And this is a Navier equation in different representation, just a split in terms of shear modulus and compression modulus. So this is a compression term. There's also a shear modulus in, not only K as a compression modulus, right? And this is a factor which is multiplied to all parts of the displacement field, which relate to the divergence, to the volumetric strain. While the shear modulus is multiplied here to twice the gradient to the displacement field, and this is the shear term. So this is the co-operator here in this notation, and times the gradient again is a kind of second derivative. So in simple or more simple generalized equation, it's a Laplacian. But here it's a co-operator, so this is a full equation actually for an isotropic material which is compressible. So we have a compression wave speed here and a shear wave speed here. And this is a balance of momentum equation, the wave equation, also called Navier equation. As said, we have based already here on this equation, we have two modes: the compression wave speed, which is propagating longitudinal, and the shear wave speed, which relates to waves which propagate transversally to the axis. This is shearing the tissue, and this is compressing the tissue. Well, and when we separate both fields by Helmholtz decomposition, just here using the co-operator or the divergence operator, right? Then we can simply solve the equation by an inversion. So we bring this part of the equation, so the Laplacian here, just to the other side, and we end up here with the shear modulus. So this is the solution of the inverse problem in time harmonic elastography, where we are interested in this shear modulus. As a drawback, I already mentioned, we have now third order derivatives. So we have to apply, prior to this solution, the co-operator, which is a numerical derivative, and then to solve the Navier equation, we have to take care for here this second order derivatives, which is a Laplacian here, right? So third order derivatives, numerical derivatives, are overly sensitive to noise. This makes solutions quite hard here for time harmonic elastography. And of course, you can also write down the equations for the compression wave speed here, compression modulus, and then, yeah, you could also do elastography to measure compressibility. The problem is, of course, the compression modulus is very high. It's in the order of gigapascal. And the compression itself, the strain, the compressive strain, is accordingly very low. So, but multiplying a very low number with a very high number, almost 0 times infinity, right, gives a finite value, and this is pressure. This is the compression wave speed, or the pressure induced by the compressive waves. And this is numerically hard to treat. The shear wave is on the order of 1,500 times, 1,000 times slower, and therefore the waves are much shorter and they can be numerically easier. Well, when we come to viscoelasticity, then an important thing happens. So we are always talking about time harmonic deflections. And if you consider time harmonic strain, then in an elastic case, the time harmonic strain would directly follow here the oscillation of the stress. So there wouldn't be any lag. While in a viscous material, it's possible that you send shear waves through a viscous liquid, which is not possible, but just in this theoretical case, then you would see a lag, which is in the order of delta t, so pi r divided by the frequency. So this is a phase angle of pi r, right? So we see a response of the material to the strain wave, which has a phase lag. And this can be quantified in the complex shear modulus. After Fourier transformation of the time mass term of the wave equation, we come to a complex valued shear modulus, where the storage modulus would here determine the direct response of the material to the stress wave, while the imaginary part determines or denotes the time lagging, the time shifted part, about a wave or a phase angle here, which is exactly what we consider as viscosity. Right? So with our complex shear modulus, we cover the storage and the loss properties of the material. And we measure always both. Biotissue is always viscoelastic. So it's all about complex shear modulus measurements. And in which way those complex shear moduli behave at different frequencies is prescribed by viscoelastic models. And we make it very simple. So we consider basically three models which have only two parameters. Three parameters alone are too complicated to us, because we have normally two independent measures, storage and loss modulus, and we don't want to overfit our equations. So stable values we gain normally with a two-parameter model, and there are basically only three two-parameter models, which is the Voigt model, the Maxwell model, and the Springpot model, shown here. And they differ in the way how we combine here the elastic representation and the viscous representation. So the spring and the dashpot. If we do it in parallel, we have the Kelvin-Voigt model. So this means when we would stretch such an element, such a circuit, we would induce the exact same amount of strain on both sides, on the dashpot and the spring here. While in the Maxwell model, we have a spring and a dashpot, and if we stretch the Maxwell model, we induce the same stress, but the strain in both elements can be different. And the Springpot model is actually an interpolation between the spring and the dashpot. I will come later to the Springpot model, because this is a model, the only two-parameter model actually, which predicts over frequency a monotonic increase of storage and loss modulus. Both increase, and this is something we always observe. While the Maxwell model can show also a decrease in the loss modulus, the Kelvin-Voigt model predicts a constant storage modulus. And neither of these cases has ever been observed in our biotissue. So this means if we stick to simple models, then go to a Springpot model, which is a power law. So power law models are preferred for the viscoelasticity of biotissue. And because I like so much the Springport model, I would give you a little glimpse how we can interpret the Springport model from a mathematical, or let's say from the structures of the mathematics. It's really beautiful, not to go into all the details here, but to see how mathematically the Springport model can be derived from the wave equation and the diffusion equation. And this is the really fascinating aspect of the math behind our research here. I told you we are concerned with the wave equation. Wave equation is second order here in time and second order in space, right? So this is a wave equation, very basic structure. And the solution here is a plane wave. It's a plane wave solution. In contrast, the diffusion equation is first order in time and second order in space, right? And the solution here is a Gaussian-shaped function. So this is a probability telling you how fast particles can randomly travel through space. How fast means velocity, meter per second, through space times another space dimension, so square meter per second. This is a dimension of the diffusion coefficient, E here. And theoretically, it's allowed that a particle at time zero is already infinitely or has infinitely traveled away. This is a probability. This would never happen with a wave equation, which is a scaling equation. Both time and space can be scaled down, and you will always see the same behavior. And this is another point why we can, with waves, scale down like in a microscope and zoom into tissue by changing the frequency, by looking into smaller dimensions, right? Well, the interesting observation we made with the Springport model is that we are in between the two here. Our waves we send through the tissue do not behave fully like consistently propagating waves. They are kind of randomly scattered due to the abundance of scatterers in tissue. And this is especially well seen in ultrasound, where the scattering of ultrasound waves is a contrast, actually. It's not the compression modulus, also it's a backscattering of ultrasound waves, which gives you contrast of tissue. And I mean, maybe 20 years ago, ultrasound images looked awful, right? So like a snowstorm, like a blizzard. I was always wondering how physicians can see disease here and detect something, right? But meanwhile, I must admit that ultrasound images are great, and especially near the surface, you have almost microscopic resolution. So this has a lot of developments have been achieved here, and this is really a good imaging model. But we come to it later today. Well, as I said, we have the equation for waves and diffusion, and for waves, we have second order in time. So the only difference is second or first order in time, right? And if we add here a parameter to introduce a fractional derivative, right? So neither 2 nor 1, then we are in between wave and diffusion, so which is called wave diffusion. And as said, this is something which happens to the waves we send into the tissue, right? Wave diffusion, diffusive properties of shear waves. And this is the explanation why we see, or why we can measure here viscoelasticity in such a very simple way, by assuming alpha equals 0 for the wave equation, or alpha equal 1 for the diffusion equation, right? And with this time harmonic assumption, right, where we Fourier transform our displacement, right, then we can assume I times omega, so the frequency to the power of alpha, right? And this is then plugged here into this equation because we are always looking at the time harmonic equation. Meaning, then we come here because alpha minus 2, 2 minus alpha, sorry, 2 minus alpha, and this minus alpha comes to this side now, to this n side, to the spatial gradient side, while the power of 2 is the standard second order time derivative here. So, and this is the Springport model. So we just assumed here any modulus kappa, so it can be the shear modulus or the compression modulus whatsoever, in front of I omega to the power of alpha. And this is the time harmonic representation of the so-called wave equation or diffusive wave equation. This is a Springport model plugged into the wave equation. This is with which we always work, right? Another very beautiful property of this representation is that we have here now our complex shear modulus with this kappa modulus. The kappa modulus actually has a weird quantity, depends on alpha, right? Therefore, we split it into a shear modulus part and a viscosity part. If alpha is 0, then we have just mu, so shear modulus. If alpha is 1, we have here just viscosity, while in between 0 and 1, alpha can take all values, and we end up with a mixture of mu and eta, so shear modulus and viscosity. And if you compare here the representation of the Springport complex shear modulus with the representation of the complex modulus as a magnitude modulus and the phase angle here, you can simply compare I to the power of alpha, very beautiful mathematics, by the way, is the exponential of pi over alpha, pi over 2, and then I times alpha. So this is an exponential, meaning we can simply compare this exponential with this exponential, and we come to the conclusion that alpha in the Springport model is just 2 over pi times the phase angle we measure with a complex shear modulus. Without any model, we take just the phase angle of our complex shear modulus, we multiply it by this factor, and then we have already the power law coefficient according to the Springport model. So this is a very effective way to solve the inverse problem in elastography directly based on the Springport model. If we interpret this phase angle as alpha from the power law Springport model. And power law means on logarithmical coordinates, it's just a linear increase, right, of storage modulus and loss modulus. And the slope is either alpha or the phase angle phi times 2. So, and this is something we always observed. So this is just an example series of brain MRE. I think it's in my brain, shaken over a large frequency range with intrinsic activation. It's just the arterial pulse wave which traverses the brain with each heartbeat, so we can harvest this deformation Fourier transform, picking out 1 Hertz components, and we have the 1 Hertz waves. This cannot be induced externally. So the lowest frequency we can treat with elastography is 5 Hertz. And then we go the way up to 40 Hertz, and we see here the decrease of the wavelengths, and we can just fit a profile to measure the wavelengths, and as the wavelength is the frequency with which we vibrated divided by the wave number, then we know the wave number or the shear wave speed. So this is quite easy. And the shear wave speed here plotted over frequency in group of volunteers compared to the literature prescribed here, such a power law which can be fitted by the Springpot model. This is a lot of old work, actually, 2010, where we compared at this time only 4 frequencies, 25 Hertz to 62.5 Hertz. So we performed multi-frequency MRE in a superimposed way. We had 4 frequencies at those days. And just showing the principle here that the point model is clearly violated by the increase of the storage modulus over frequency, right? The Maxwell model is violated by the increase of the loss modulus over frequency, while the Springpot model reasonably well describes that we see an increase in both. This is an experiment where we designed a phantom. It's just a PAA, polyacrylamide, not cross-linked. It's liquid. So this is a liquid material which was designed to mimic the viscoelastic properties of healthy liver, of healthy human liver. Of course, healthy human liver is not liquid, but in the frequency range we are normally examining. So we test frequencies from 5 to 100 Hertz or even higher in the tabletop MRE up to kilohertz. In this frequency range, the behavior is quite well reproduced by our liver data. So this is just measured by different modalities here, reproducing the increase of shear wave speed over frequencies in different modalities from shear rheometry to tabletop conferences. But interestingly, the Springpot model is good in our frequency range, but cannot predict static deformation of the liver, right? Because it's a power law which approaches zero shear modulus at static conditions with zero frequency. It's undefined in this range. I mean, interestingly enough, that despite this weakness of the Springpot model, the range of frequencies is quite well covered with the properties of such a liquid material, which is a Springpot-like material from very low frequencies, even lower than 10 Hertz. Well, the Springpot model parameters, storage modulus and power law exponent alpha can be thrown in such an two-dimensional parameter space. So, and this is quite generic. So we can also call it kind of stiffness-like property, shear modulus, storage modulus on the y-axis here, or power law exponent or phase angle of the complex shear modulus on the other hand, which is also called fluidity from sometimes. So this is something which actually we invented, this term fluidity, to explain to the physicians what this, our viscosity parameter means. So we cannot come up here with alpha or power law, they don't understand, but fluidity is something they can understand. If this phase angle phi or alpha is 0, and I said it's purely elastic, while with alpha equal 1 or phase angle equal pi over 2, it's a liquid material. So with increasing phase angle or alpha parameter, we move our material from an elastic solid more to a liquid-like material. So it's a phase transition, actually. So with alpha equal half the phase transition point. And there are relationships to structure. I will maybe show here on this slide. This is, I mean, looks funnily colorful, but there are tons of data behind. which show in the human brain how stiffness and phase angle, so elasticity and fluidity change over different processes and disease. For example, with aging, we see an increase in stiffness and a decrease in the fluidity, while most brain diseases are associated with softening. So it gets always softer, and the fluidity is also decreasing in most cases, which we have investigated so far. So Alzheimer's disease, Parkinson's disease, normal pressure hydrocephalus, and in some disease like in multiple sclerosis, we saw even the reverse of the parameter of the mechanics of brain mechanics after treatment. Or as multiple sclerosis has disease causes which are remitting, relapsing, it can also it can improve. Symptoms can improve, and this is also associated with an reverse and restorage or reinstallation of the original biomechanical properties of the brain. Rafaela will show later some data on that. Well, maybe this is a bit too complex now. The limits of the Springport model, just a little glimpse into such dispersion curves, shear wave speed over frequency. We can have crossing points across different regions, so that in the mouse brain, in the kilohertz range, the hippocampus is stiffer than the corpus callosum, for example, while in the human brain at lower frequencies, so in the range of 50 hertz, we always see the flipped behavior between corpus callosum and hippocampus. And with ASN, it's more to our frequency range in the human brain. So we see even the mouse brain the same. So it's not related to the species, so mouse brain versus human brain. It's related to the frequency range. And those crossover points are, of course, not predicted by the Springport model, but by another level of complexity, an additional element here, spring or dashboard, which would then predict such a behavior. Well, this is an example actually for our current brain MRE in clinical use for the characterization of brain tumors. And brain tumors are a good case because they differ dramatically in fluidity, so in the phase angle between the more malignant cases and the more benign cases. The reason for that is still under investigation. I don't want to reveal it here, but I would like to show a case where it was clear by looking here at the MRE shear wave speed map, at the stiffness map, in combination with the fluidity map, here the phi angle, that this cannot be a glioblastoma, which is a highly malignant brain tumor. And as I showed here on this slide, the malignant cases are on this side. So this is here the phase angle of phase transition between more dominant solid properties and dominating fluid properties here. And in the lower phase angle range, we see all our malignant cases. So when we encounter high phase angle, we can be pretty sure that this is not such a malignant tumor. And Mergan showed me this case and told me this patient received 3 times MRI, standard MRI with contrast agent in order to clarify if this is a glioblastoma or a meningioma or any other entity. And based on the standard MRI, so with ADC and T2 weighted imaging, the radiologists and the neurosurgeons, they agreed upon this is a glioblastoma, and this patient was treated as with glioblastoma, and then they found it was a metastasis of a lung carcinoma. So this patient would have received totally different treatment with chemotherapy, etc. If they would have taken here the biomechanical properties of these tumors more seriously. Well, what is actually the time limit? So I'm running.
Would have been 10.
It would have been 10. Sorry, I thought 10. Okay, but I think you got already a glimpse into the ideas of our biomechanical frameworks we are dealing here with in MR elastography and ultrasound elastography. And I think you deserved a break. I'm here around, so if you have questions, maybe 1, 2 urgent questions now, otherwise we can talk later on the break. Okay.
I mean, it's not an urgent, I don't know what answering an urgent question, but I just wanted to know, what do you mean when you say kidneys have more water than blood? What does
just if you try the kidney, so try it out, right? So totally, so put it in a kidney sample into an lyophilizer, right? Where the water is evaporated entirely, right?
So
and then you measure the dry mass versus the wet mass. You get a quantitative amount of water, and this quantitative amount of water in the kidney is higher than you would take a blood sample.
I mean, I still don't like blood is a low, right? And if I
but the water content, and this is the point I would.
It's some hematocrit. Now, if I even then dehydrate the hematocrit, you're saying that dry mass is lower than the kidney cell. So kidney cell.
No, the dry mass is higher than in the kidney after. If you take, for example, a liter of blood versus a liter of tissue from the kidney, right? The dry mass of the blood would be higher than in the kidney.
Right. So blood cells themselves have more internalized.
Yes.
Than kidney cells.
No, they're not water. No, they have more solid structures. More proteins, iron, etc. What is in the blood, right?
Yeah, that makes sense.
Well, I mean, in the kidney, the structure makes the difference, the mechanical difference. So the shear modulus is not related to the water content. So this is the take-home message now. Thanks for the question. Grab the coffee. Thank you.